Hi, everybody. We're continuing in 3.4. This is part two. And I want to start with just some like more, like some definitions and stuff and more formalized theorems and so forth. Then we'll go back to doing some more problems. Okay, so let me switch my go. Where are we? Okay, here we go. So this substitution method is is a way of basically it's kind of like the chain rule backwards. So here's what I'm saying. We know that the derivative of f of g of x is f prime of the big function g of x times g prime of x dx. That means that if I'm starting with something that looks like, uh, if I'm starting with something that looks like this, just this part over here. If I'm starting with that, which is what we have over here, and then I integrate it, I get back to this. That's kind of what it's saying. And the way we make it simpler to see, we make a substitution, let u equal g of x. That kind of shortens it, makes it a lot shorter and sweeter and easier to see. So du dx is g prime, du is g prime dx, which is what I have in the integral g prime dx, and and this here is going to be f prime of u, and it's going to be nice simple. Here we go. Let's just say so. It winds up being f prime of u because it's f prime of g of x times g prime of x dx, which winds up being f prime of u du, which is beautiful. And now this is going to be easier because it's going to be a lot easier. So when you see a product, in the integral, especially if you recognize that one factor is a derivative of some part of the other factor, that's basically when substitution is going to come into play. So what you do is you, again, just to state it more formally. I'm going to give more examples in a minute. The goal is to turn the integral of f of g of x dx into f of u du, where f of u is much less messy than the f of g of x, and messy, hence easier to do. So u is going to be some part of the integrand, and usually it's the step inside the messiest bit, meaning it's like the function inside the function, it's the inner function, so to speak. And so du is du dx dx, and then you just switch everything. You translate your x's into u's, and you get an easier integral, and then you back substitute, and it's all going to work out. But again, it's let's do more examples, and everything will be more clear. So let me stop the share, and we're going to do another example right now. Okay, this is an interesting contrast because here's two integrals which look almost identical. As you can see, except they're upside down of each other. Despite that they look almost identical, they're solved. Yes, they do have different solutions, but the way they're solved is extremely different, as we're going to see. So the first one, a, that we're actually going to do a u substitution. So for a, so the integral of x squared over x cubed plus 5 dx. So we're going to let u equal this bottom here, x cubed plus 5. And I'm doing that because I know when I take a derivative of this, du is going to be 3x squared dx. Now here I have an x squared dx, but what about that 3? I don't, that 3 is not part of it. So what I'm going to do is I'm going to divide both sides by 3. And I have 1/3 du is equal to, so let me just rewrite it a little nicer. 1/3 du is equal to x squared dx. So when I have that x squared dx, I'm eventually going to substitute, I'm going to swap that out for 1/3 du. And this guy down here, x to the third plus 5, that's just going to be u. So this is going to equal now, this is going to equal the integral of 1/3, I'm going to bring the 1/3 out, of du over u. And that's the whole thing. So this here equals that, because the x squared dx is 1/3 du, and the x to the third plus 5 is the u that's on the bottom. And this is just equal to, of course, 1/3 ln u plus c. And now when I back substitute, that's going to equal 1/3 ln of x cubed plus 5 plus c, and that's my answer, and I'm sticking to it. Ready. Now for the next problem, though, it's going to be very, very different. The second problem, because I can break this up into two fractions, is going to be a totally, totally different. Actually, really, I guess I would say even much easier. So this is going to be x cubed over x squared plus 5 over x squared dx. Now this, of course, is just the integral of x plus 5x to the negative 2 power. Again, all of that dx. Well, the integral of x we know is x squared over 2. And the integral here is going to be 5 times so it's going to be 5. The integral of x to the negative 2 is x to the negative 1 over negative 1. And of course, plus c. And I'm just going to write this a little bit nicer. X squared over 2 minus 5 over x plus c. And that's my answer. And I am sticking to it. Here's an interesting problem. Let's look at the integral of ln x over x dx. Now, where's the u substitution? I don't see it. Well, you know what? If u is equal to ln x, then du is equal to 1 over x dx. Now, I have a 1 over, that's what this is right here. That's 1 over x dx. So this now becomes the integral of u, of u du. Because ln x is u, and x dx, or with the x on the bottom, is du. And this is just going to be u squared over 2 plus c, which equals ln x, the whole thing, squared over 2 plus c. And that's amazing. That is the answer. Now this one, it's so, this was so, to me, this was so, I don't know, unexpected or counterintuitive. I want to work this out. I want to start with this and take the derivative and show that we get this. So let's look at, so let's say y equals ln of x squared over 2 plus c. So what is y prime? Y prime, well, this is really a chain rule. So the 2 comes out front. It's really 2 ln x, and of course it's still over that 2. And then times the inner derivative. Now the inner derivative, so this is the outer, that's the out right there. And I have to multiply it times the inner derivative. The inner derivative is the derivative of ln x, which is 1 over x. And when I take the derivative of c, it just disappears. But here the 2's cancel, and this just becomes ln x over x, which is what I started with, in my original thing. So this, as weird and wild and wacky and crazy as this is, it actually worked. How do you like that? Okay, I'm going to stop this video here because the next video, I'm going to make a part 3, and that's going to be also integration, using substitution, using this strategy. The difference is that so far, all the examples I've been giving you have been indefinite integrals. Now we're going to give examples with definite integrals, and there's going to be a little bit of a little tweaking that has to be done. Nothing horrible, nothing serious. And I will show that all in the next video, and can't wait to see you soon. Bye.